We're starting a new chapter, the next chapter after the electromagnetism, which is photons and photoelectric effect. This is a pretty interesting chapter, and there are some almost all of the contents of this chapter is new, are new. So yeah, let's just jump in directly. The first thing that we're gonna discuss is তো এগুলো হচ্ছে মোরলেস আমাদের ডিসকাসেবল টপিক। তো আমরা এক পাশ থেকে শুরু করি। ফার্স্ট অফ অল, what is light? Is light a wave or is light a particle? What is light? There has been some historical dispute about the nature of light. It has been going on for a pretty long time. The first recorded opinion for any from any renowned scientist that we have is from Isaac Newton. Sir Isaac Newton, without any physical evidence or without any experiments, out of hunch, he guessed that light is actually made up of particles. Different colored objects have different size and shape of these particles. Whenever these particles come and hit our eyes from that object, then we can see different color of that object. It was a total guess. He didn't have any experiment or setup to prove his theory or hypothesis, should I say, because it was not proven. But because Sir Isaac Newton was such a renowned scientist and he was such successful in many other fields, this idea went on going for a really, really, really long time. Then the scientists started to, as science progresses slowly, people came to learn more about waves, and eventually they seem to understand that uh, many of the behavior that a certain type of wave does, for example, reflection, refraction, those kind of things, diffraction, the spreading out when going through a slit, such and such. Scientists found out that the behavior of light is similar to many of those things. So at this point, scientists decided that light should be wave. It should not be a particle. But back then, the idea of only physical wave, or what can you say, the mechanical wave was only prominent. People still didn't have idea that wave could also go from one place to another place using through vacuum. So the idea of electromagnetic wave was not yet discovered or proposed. So scientists assumed that wave light is a wave, but because light could travel through apparent vacuum, because from the sun to earth and in other places as well, so they assume that the entire universe is filled up with a very, very low density, ever present medium called ether. It's a hypothetical medium. They just came up with this idea because they had to substantiate, or they wanted to prove that light is a wave. But because every wave requires some medium to pass from one place to another place, they assumed the presence of this medium ether. And also this ether was also present inside the atom, where there was empty space described by scientist Dalton in his theory as well. So that idea went on for quite some time. Then James Clerk Maxwell, he came up and showed that there is a light can the waves can also happen in the form of electromagnetic waves. Electromagnetic waves mean oscillating electric and magnetic fields together can give us the presence of wave. And for electric field and magnetic field variation or electromagnetic wave to travel from one place to another place, it does not require any medium. It can very easily travel without the presence of any medium. The variation of electromagnetic fields, electric fields and magnetic fields simultaneously does not require any medium. So when this idea was checked and through experiment it was proved, then scientists stood corrected that, okay, fine, we're gonna call light to be electromagnetic wave. It is still a wave, so but the presence of this hypothetical medium ether was obliterated. That we don't need the presence of this undetectable medium ether, like because light is an electromagnetic wave, so it can travel from one place to another place without the presence of any medium. This idea also went on for quite some time. Then scientists, as science progresses further, the scientists stumbled upon one very specific uh, incident of light experiments, which is called photoelectric effect. The idea of photoelectric effect is something like this. There are certain elements, I can say material, there are certain elements which has the property that if you have if let's say this is the surface of a certain element. It was found through experiment that whenever we shed light onto this uh, surface, this is our metal X. Whenever we shine light upon this metal surface X, uh, for a certain property of this light wave, for a certain property, this property is actually frequency, but for that I'm using only the word property. For a certain property of this light wave, these metal piece tend to give up free electrons. So whenever light falls onto it, it tends to release electrons. This basic happening of giving out light-based electron is what is called the photoelectric effect. So the name pretty much suggested photoelectric. Photo means light, electric means something that produces electron or something that is related to the flow of electron. So together they make photoelectric effect. So that's the idea. So we have that information. So scientists found out this happening. Finding out this incident of photoelectric effect was not a big deal. When scientists started to do rigorous experiments on the photoelectric effect, then they came up with some pretty uh, disturbing observation. I'm saying disturbing because at this point, the of the experimental finding of photoelectric effect were totally inexplicable using the electromagnetic theory of light. Electromagnetic theory means where light is defined as a electromagnetic wave. The photoelectric effect was not actually buying in or agreeing with that theory. So scientists are quite perplexed and they're puzzled that what is actually happening. Pretty soon, uh, Max Planck, he's also another scientist. Max Planck gave an idea. He was a very ill-known scientist. I mean, not such a big scientist or anything like that. He published a paper that light rays could be actually particles. And he gave he proposed some theoretical aspect and calculation regarding that in a small paper, but that did not shake up the scientific community. No one actually pay heed or even take into account his paper that light could still be particle. He named those particle photon. He was the person who coined this term photon. Uh, then Albert Einstein came in, and what he was saying that if we consider the idea of Max Planck to be correct, if we do take light is actually particulate, that it is divided into small particles which are called energy, which are called photons. Uh, we can very easily explain the behavior of the photoelectric experiments. So what he did is that he took Max Planck's idea and explained the photoelectric effect experiment outcomes very effectively, logically, and coherently. Coherently means the logic was not not opposing each other within the discussion. So it was also foolproof kind of explanation, and he did that. So he took Max Planck's idea of particulate nature of light and proved and explained the outcome that scientists obtained from the rigorous experimentation of photoelectric effect. So he was awarded the Nobel Prize in 1905 because of his contribution on the explanation of photoelectric effect using Max Planck's theory. Albert Einstein was not awarded Nobel Prize for his general theory of relativity, because back in that time the effect or the or the ever growing weight of the theory of relativity was not understood by most scientists. People just saw it as a theoretical venture or something like that. But as time goes by, people are doing more research. They are finding out that yes, the theory of relativity is actually a pretty strong thing. It touches a lot of different aspects of science. So that's why when Albert Einstein, when the Nobel Committee in 1905 was trying to look for something to award towards Albert Einstein, they found out, fine, this is a good idea because he actually solved a pretty big mystery that has been going on in the scientific community for quite some time. So in that process of explanation, to be honest, Albert Einstein didn't discover or invent anything. He took the idea of Max Planck, who was a really less known scientist, and then used it to explain photoelectric effect. And he was awarded the Nobel Prize. Max Planck was also awarded Nobel Prize, I think that year or the year after, for his idea of particulate nature of light. And then, so that's what happened. সেখানে আরেকটা জিনিস আমি লিখতে ভুলে গেছি। এটা আমাদের লাগবে, এটা পরে বলতেছি এটা কি জিনিস, de Broglie equation. So that's pretty much what happened. So that's the history. That's a little bit of historical background that how the idea of light has been changing over the years in human civilization. Now let me discuss actually what happens in the photoelectric effect. What was found in the case of photoelectric effect. First of all, The scientists had an experimental setup. I'm not going to draw the whole experimental setup, but what I wanted to understand that, let's say, this is the surface of a metal. So I'm not going to use this. Actually, I can use actually this surface. Let's say this is a cuboid of a metal or a trapezium shaped metal, and there is a physical way by which we can actually observe the current flow over here. Let me just draw the phototube. Drawing the phototube might be a good idea. Come on. Come on. এই ব্যাটারির পারপাস কি হবে সেটা পরে আলাপ করতেছি, আপাতত জাস্ট একটু সার্কিটটা আঁকি। This setup that you can see over here, আচ্ছা এখানে আরেকটা জিনিস আমি আঁকতে ভুলে গেছি, সেটা হচ্ছে okay. So this is a glass tube within which we have a metal plate. Let's say this is one of the metal plate. Let's label this metal plate as metal plate X. And we're going to shine in some light from outside the tube through the side of the tube onto the metal plate, and we're going to observe what happens to the circuit. Now let me explain how this circuit is working. Currently the battery switch is open, so there is no voltage applied across these two plates. So for disregard the lower part of the circuit for the time, মনে করো আপাতত এই lower part টুকুর কোনো কাজ নাই, এটা আমাদের পরে কাজে দিবে। So we have a microammeter that is attached from here to here. This is a very sensitive emitter, like a super sensitive emitter, maybe even a couple of electron sensitive. So even if even if there be a slight flow of electron variation, this emitter can give you some instantaneous reading. It's a very sensitive emitter. That's why I use the term microammeter, very sensitive emitter. And we're going to shine light upon it. The idea is, if photoelectric effect happens onto this metal plate, the produced electrons, they are actually gonna shoot themselves out of the surface of this metal plate X in random direction. What I'm trying to mean is that if this is the X bar, X plate, and if we shine light, whenever the electrons are gonna come out, the electrons are not going to only go straight like that. They are going to go like this. Some of them are going to go into the towards the inside of the metal piece. Some of them are going to come out like this. So the coming out of the electrons, which we call photoelectrons. Photoelectrons basically means they're still electron, but they're produced by means of light. So the photoelectron basically is a term that is specifying the generation process of those electrons. For example, we have also seen thermal electrons. For example, if you remember the idea of electron gun in a cathode ray oscilloscope, electron gun, how did we produce the electrons in an electron gun? We produce them by thermionic emission. We heated up a certain metal coil to such high temperature that the electrons could have enough energy to be free of the metallic bond, and they could actually become free of the metallic coil. So in that case, heat was supplied to dissociate the electron from the original metal. In this case, light is used to do the same thing. So now we are calling them photoelectrons. So these photoelectrons, they are going to be released in random directions. So we're totally okay with that. Whenever the electrons will shoot in random direction, it is quite possible that some electron will ultimately hit this right side plate. Some electron can come in and eventually hit this right side plate. So whenever the right side plate will be will actually take some electron, and as the electrons will be leaving from this plate will slowly become positively charged, and this plate is essentially in this case neutral because it is not losing anything. So there will be a potential difference across them. So the moment the electron would be over here, that electron is going to flow through this wire, flow through the emitter, and eventually turn back up over at the X plate. So which means because there is a voltage difference, this plate will slowly become more and more positive by losing electron over time. And so whenever any electron, any photoelectron will ultimately hit this right plate, it will prefer to travel through the circuit and eventually reach up to the left plate once again. So that will produce a small bit of current, and we can see that this current will happening. So the idea is that if we shine light over here, if the light has the necessary property, which is a bit high frequency, then we'll see that the micrometer is giving us some reading. So having some reading in the micrometer means that this plate is actually bursting electron. It is actually producing photoelectrons, and because some of those photoelectrons are getting absorbed on this right plate, the micrometer is capable to give us some reading. So the observation of the micrometer reading actually logically leads back to the production of photoelectron or photoelectric effect. এই কনসেপ্টটা বুঝা গেছে কিনা এই পর্যন্ত?
Yes, sir.
ওকে, কারো কোনো কোশ্চেন থাকলে অবশ্যই হাত তুলো, বা কোনো কোশ্চেন থাকলে অবশ্যই জিজ্ঞেস করো। আল ট্রাই টু রি-এক্সপ্লেইন, নো বিগ ডিল। আচ্ছা, এরপর যে জিনিসটা আমাদের লাগবে সেটা হচ্ছে বুঝা লাগবে, সেটা হচ্ছে যে what is the property required for the photoelectric effect to happen. What was found out in rigorous experiment is that photoelectric effect actually has a couple of properties. Let me just write it down, those properties. Number one property that was found out, that there lies a minimum frequency of the light. There lies a minimum frequency of the incident light for which photoelectric effect happens. There lies a minimum frequency of light for which photoelectric effect actually happens. If the shine light frequency is higher than that value, then photoelectric effect will still happen. But if the light's frequency is lower than that value, then photoelectric effect simply does not happen. And when an intensity of light, intensity জিনিসটা কি সেটা আমি একটু পরে আলাপ করতেছি। Intensity of the light source does not have anything to do on the photocurrent. Lower than the at frequencies lower than the threshold frequency. Threshold frequency is basically what we mean by the minimum frequency. Threshold frequency symbol হচ্ছে f not নাকি ft, না f not মনে হয়, Yeah, this is what we call a threshold frequency. Threshold basically means starting. Sandy just picked up this word. So the threshold frequency is the smallest frequency at which the photoelectric effect for a specific metal happens. Uh, Anything that frequency, any light of that frequency or in frequency higher than that frequency does give out photoelectric effect. But any light source with lower frequency does not give out photoelectric effect whatsoever. That was the observation. And intensity. Achha, let me just define what intensity is. Intensity is defined as a physical quantity which is given by power over area. The unit is watt per meter square. So intensity is basically telling us how much energy is delivered to a certain surface every second into its unit square area. So it is basically a measure of the energy supply rate or energy receiving rate of a certain surface. If the intensity of if the intensity of light on a certain surface is high, it means it has a large number of uh, a large amount of light energy is falling onto this thing. For example, if I give you a very bit very usual idea, uh, on the midday the sun's intensity is pretty high because we feel pretty warm. It's because the rays are falling vertically. So the energy is hitting at a pretty concentrated form. But on the dawn or in the dusk, uh, the sun's rays actually hit the Earth's surface at some pretty steep angle. So the energy concentration is actually not that high. So the intensity of the light ray is also pretty weak. And intensity is also dependent upon distance. If you go further away from a certain heat source or from a light source, the intensity gradually decreases because the light spreads out or heat spreads out, which you already know from heat sources, that if you put your hand close to the stove, there is a certain distance beyond which you cannot reach comfortably, because your hand starts to feel uncomfortably warm. So beyond that level, you can put it anywhere and experience the heat comfortably. And what you'll also find out that the farther you take your hand away from the stove, burning stove, the less temperature that you feel, because the temperature or the radiated energy, it tends to spread out. So if we are further away, we get a smaller fraction of the original energy. So that's the idea of intensity. So one simple way to understand how does intensity work for any light source is that if we take identical sources, and let's say if you have one light bulb, the amount of let's say you have one light bulb and you have one specific metal surface right over here. So let's say this surface has certain value. You can choose not to measure anything or not to calculate anything, but let's say you are placing one light source right over here, and this is a metal surface, and you have some intensity of light falling onto this surface. Light is actually going in every direction, but a fraction of that light is actually hitting our metal surface, so we have that. Then if you bring an identical light source right beside it, identical light source, you're simply gonna make the intensity double, because now two light sources of equal energy are shining light onto the surface. If you bring up another one, you're going to triple the intensity. If you bring up another one, you're going to make quadruple the intensity, so on and so forth. So you can increase the intensity of a certain surface simply by increasing the number of light sources. And also in the same way, if you reduce the number of light sources, you will reduce the intensity as well. That's one very simple way to change the intensity of a certain surface. It's very simple. It's like, let's say within a room, you have multiple light sources. If you turn up only one light, you feel it to be somewhat bright. But if you turn up two lights at the same time, then the whole room starts to look better, or it looks at least brighter. So that's basically increasing the intensity. So the idea of intensity is said. So what the scientists found out, that the number one observation says that there is a minimum frequency or threshold frequency existence, that at a certain frequency or above that value, the photoelectric effect happens. Below that frequency, photoelectric effect simply does not happen. That's the first observation. And the second observation goes like this. I actually forgot the second observation. Amar. একটা বুকলেট পেলে ভালো হতো। আচ্ছা, বুকলেট তো এখানে নাই। তাহলে এখন আমাকে কি করতে হবে? নোটস দেখতে হবে। নোটস কোথায় আছে? ও নো, বলবান তোমরা একটু এই বুকলেটের ভিতরে দেখো তো 1 নাম্বার অ্যাজাম্পশনে কি আর কিছু লেখা আছে? আচ্ছা, আমি পুরোটুকু একটু বলি। পুরোটুকু বলে নেই, তারপর কম্পেয়ার করলে হবে। অ্যাকচুয়ালি বুকলেট আছে হচ্ছে অফিস রুমে। আমি এইখানে পুরা জ্যাকটিন হয়ে বসছি উইথ দ্য মাইক্রোফোন এন্ড এভরিথিং। আচ্ছা, আমি একটু পরে বুকলেট আনতেছি, সমস্যা নেই। The second observation of the experiments was that the intensity of the light sources. So let's say number 2. The intensity of the light sources didn't have any effect on the photocurrent. Photocurrent means what would be the reading of this emitter. This is what is calling photocurrent. The idea is very simple. As you can see, photocurrent basically means the current that is produced out of photo, which means the current that is made because of light. So if we have a much higher rate of photoelectric effect, or rigorous or too much happening photoelectric effect, we're gonna have many electrons sitting up over here every second, and then that's gonna give rise to a higher photocurrent. If you have less photoelectric effect, then less photocurrent, so on and so forth. So the measure of this photocurrent is actually a way to tell that how many photoelectric effects are happening over here. It's not the exact number, but that's a pretty good approximation. A big amount of photoelectric effect will definitely give rise to a high photocurrent and vice versa. So the second observation says that uh, below the threshold frequency, the intensity of the light source does not have any effect on photoelectric effect. What it means is that let's say that the threshold frequency of this material X is 1000 hertz. I'm just choosing a random number. Let's say that in the threshold frequency of this material is 1000 hertz, which means light rays of 1000 hertz and higher will give us photoelectric effect, and below will not give us photoelectric effect. The second observation tells us that be, below the photoelectric effect frequency, the intensity simply doesn't have any effect. It means if I choose to, if this is my X material, and if I choose a light source that is of 900 hertz, and if I choose, let's say, 10 of those placed side by side, giving us light on over here, this plate will not give us photoelectric effect whatsoever. So no matter how many you attach, as long as their frequency is below the threshold frequency value, intensity increase will simply not matter. Photoelectric effect will not happen, period. However, above the threshold frequency, above the threshold frequency, higher intensity of light source leads to higher photocurrent. মানে হচ্ছে যদি আমরা 1000 হার্টজ এর বেশি ফ্রিকোয়েন্সি লাইট সোর্স ইউজ করি, সেই কেসে যত বেশি লাইট সোর্স ইউজ করব, মানে যত বেশি ইন্টেন্সিটি দিব, আমাদের ফটো কারেন্ট তত বাড়বে। ফটো কারেন্ট তত বাড়বে মানে হচ্ছে আমাদের ফটোইলেকট্রিক ইফেক্ট হওয়ার রেট তত বেশি হবে। এটা হচ্ছে সেকেন্ড অবজারভেশন। মানে হচ্ছে ইন্টেন্সিটি ডিপেন্ডেন্সি নিয়ে আমরা আলাপ করতেছি। বিলো দ্য বিলো দ্য threshold frequency, there is no effect of intensity whatsoever. Above the threshold frequency, the intensity of the light source is directly related to the amount of photoelectric effect happening on the metal surface. And then number 3 observation goes is that what the scientists also found out by keen observation, that the photoelectric effect happens to be an instantaneous happening. The photoelectric effect happens to be an instantaneous happening. It means if photoelectric is likely to happen, for example, if we have shine, let's say onto the surface, light rays of 1050 hertz of frequency of light, so we know that that photoelectric effect will happen. What the scientists found out that I mean the time delay between shining the light over here and the emitter giving us a reading is practically zero. It means the photoelectric effect is apparently an instantaneous happening. Light falls the electron immediately comes out. There is no such thing of a measurable time delay of maybe a 1 millisecond or half millisecond, like that. That light is falling in, falling in, falling in. Some time goes by, and then one electron pops up. Nothing of that sort. The photoelectric effect happens to be an instantaneous happening. This was also another very important observation. Now, these three observations, actually perplexed the scientists a lot, because they could not explain this behavior using the wave theory of light. Now, let me tell you a little bit about in detail about what is the idea inside the wave theory and the photon theory of light. So let's just go a bit sideways and discuss that thing first. So, wave theory and photon theory. The wave theory of light actually proposes that energy from an illuminated source, from a light source, comes in a continuous pattern. Continuous pattern means something like that, something of a continuous variable that is flowing without any break. A very common example that I can give you is that if you turn up the tap of your basin in such a way that the water flow does not break before it touches the base of the basin. So there is a continuous water stream, and you can see it is crystal clear, and it's just flowing all the way down without breaking. If you turn up your tap to that level, which is very possible, many of you have done it intentionally or unintentionally, so that's sort of like a representation of continuous flow of energy from a source. So wave theory proposes that the energy flow from a certain source happens in a continuous way. And that's the idea. Whereas the photon theory proposes, no, actually energy comes out of a certain illuminated source in small packets or in small particles. So they're like the droplets out of a shower head, sort of like that. So if you have an illuminated source, you're gonna have showers of small packets of energy out of that source. Now, what should be the size of each of those energy packet? That was also given by Max Planck. He said that the size or the energy, I'm using the word size in this case, I'm actually meaning the energy content. The energy content of each photon, so I might as well write energy of each photon was given by the expression E equals to HF. F is the frequency of the light source, and A and H is what we call Planck's constant. So you might wonder that it says frequency. Okay, we can understand what is the frequency of a light source. We can measure it, and H is a constant, Planck's constant. So Planck came up with this idea. It's about 6.16 to 10 to the power minus 34, I think, joule second. I think that something like that. The value is mentioned in the formula booklet, so you don't have to memorize it. So this is the energy of one photon, or is given by this expression. So this equation what actually dictates that if the frequency of the source is high, then the energy content of each photon will also be high, because H is an universal constant. Universal constant means it's a constant that is somewhat similar to the gravitational constant. You know that gravitational constant is an universal gravitational constant because it is independent of place, location, or measurement technique. If you have 1 kg object placed across 1 meter distance, they will essentially attract each other by the magnitude value of Newton forces, that is gravitational universal gravitational fields, universal gravitational constant. And this measurement is repeatable, and this will be true measured anywhere in the universe. That's why we call it an universal constant. H, Planck's constant, is also such a thing. And recently, Planck's constant was actually introduced into using one of the fundamental quantities of physics, which is mass. up until very recently, this is I'm going a bit sideway to talk a little bit about the Planck's constant. Up until very recently, the unit of mass, 1 kilogram, was defined using a physical object that was located in the Bureau of Weights and Measures in Switzerland somewhere, or Sweden somewhere. So we actually measured the actual kilogram from that content, from the content of a very specific platinum iridium cylinder. Scientists were not okay with it because constants should not be defined using physical objects. They should be defined using the physical constants of the nature. So they have been trying to achieve this for a pretty long time. Recently, I mean, not so long. I think it is about 2 or 3 years that the scientists actually did use the Planck's constant in the definition of 1 kilogram mass. So now we define 1 kilogram mass by some measurement, by some involvement of the Planck's constant. I forgot the exact definition, but I saw it somewhere in the internet and was pretty delighted about it. So that's how Planck's constant, this natural constant, was introduced in the unit system. However, this is the equation that defines the energy of one photon, E equals to hf. So this is a pretty important thing. High frequency light source, more energetic photon. So less smaller energy light source, less energy photon. So one way you can possibly visualize this thing is that, let's say you have a shower head that has very tiny holes, like small holes. So if you actually turn up the shower, you're gonna have a very fine mist kind of droplets, like not so large droplets. I mean, as the water comes out, it's gonna appear slowly, like a cloud or something like that, because the droplets are gonna be so small. And in, let's say, in another case, a shower head has large size holes. So whenever you turn off the shower, you actually have big droplets of water falling onto the ground, like a typical shower that we expect. So the whole size of the shower head actually determines that whether you're going to have large size droplet or small size droplet. So something like that, something like that, that the energy content of each photon of a certain light source is determined by the frequency of the light source. If the light source has a higher frequency, then each photon will be more energetic. If the light source has a lower frequency, then each photon will be less energetic. I'm talking about monochromatic light source because I'm using only one F. For light sources which are made up of multiple lights, for example, if you consider a compound light source, for example, a white light source, then what will happen that we'll have a merge of multiple different photons together. They will be individually distinguishable, but they will come uh, as if they are joined together to give us the total sensation of white light. So we're going to have the all the frequencies or all the individual packets of energy available in the white light. That's how the white light will have. However, the explanation of the white light in particle theory is slightly more complicated than you can think. So it's not entertaining in your syllabus. I'm just telling you that even for compound light sources, the particle theory or photon theory is still applicable. I'm just telling you that. So these are the two basic idea of these two theory. Wave theory proposes that energy flows continuously, and photon theory says no, energy does not flow continuously. Energy comes in small packets. One of this packet means a fixed amount of energy. So the flow of energy means if you receive one packet, you get certain amount of energy. If you receive two packet, you get double that amount of energy. You cannot receive any fraction in between. The amount of energy that you'll receive from a certain illuminated source will always be an integer multiple of the energy of one photon, because you cannot receive half photon. There is no such thing as that. You will either receive one photon, two photon, three photon, 1 million photon, 1,000,000, 1,029 photon, something like that. But your received energy will always be in full integer multiple of that single photon's energy value. So that's the idea of photon theory. Now, let's see, how does wave theory messes up this idea, and how does the photon theory actually helps us? The first thing, what wave theory proposes is that because energy flows in continuously, like a stream of energy, whenever light will shine onto a metal piece, try to think about it. Let's say we have a metal piece, light is shining upon it. So we have light. metal light. হ্যালো, আমি ক্লাস নিচ্ছি। না, আমি 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 ক্লাস নিচ্ছি। ক্লাস শেষ করে কথা বলি। সরি। কি বলতেছিলাম? হ্যালো। আচ্ছা। Uh, হ্যাঁ, how does the Web 3 misses and how does the photon theory become successful? The Web 3 proposes that the light will supply energy to the metal atoms or the electrons of the metal atoms in a continuous stream pathway. So there will be no break. So what it proposes is that every electron is essentially attached with the atom with some energy. What we typically call in chemistry, we call that ionization energy. That you have to feed the electron that much energy somehow, either by either by light, either by heat, or by some other way. You have to if the electron is given that much energy, then the electron can overcome the attraction of the atom and become free. This amount of energy is what we call the ionization energy. The atoms which has less small ionization energy can work as a really strong very strong metals. For example, the group one, lithium, sodium, potassium, rubidium, cesium, francium, they can give up their first electron very easily, very small first ionization energy. So they are very reactive in that way. And so on and so forth. So this idea of what we call ionization energy in physics, or for the case of photoelectric effect, we're going to call it work function. Work function. The definition of this term work function goes like this: the minimum amount of energy, we use the term minimum because we want to specify in physics, the minimum amount of energy that is required by an electron, by an outer shell layer electron, to become completely free from the attraction of that atom is what we call work function. I'll say it again: the minimum amount of energy that an electron requires to become completely free from the attraction of that atom is defined as the work function. So a work function is basically an amount of energy, the minimum amount of energy by which the electron can dispatch itself, or it can make itself free from the attraction of the atom. এখন কথা হচ্ছে এই ওয়ার্ক ফাংশন টার্মটা আমি কন্টিনিউয়াসলি আপকামিং পার্টটাতে ইউজ করব. সো every element has a certain value of work function. এখন মনে করো একটা সার্টেন এলিমেন্টের ওয়ার্ক ফাংশনের ভ্যালু হচ্ছে মনে করো 5 জুল। 5 জুল মানে হচ্ছে কি, যে এটার আউটার শেল লেয়ারের ইলেকট্রন কে যদি আমরা 5 জুল এনার্জি সামহাও দিতে পারি, তাহলে সে অ্যাটমের অ্যাট্রাকশন ওভারকাম করে অ্যাটম থেকে বাইরে হয়ে আসবে। দ্যাট ওয়ে ইট উইল বিকাম এ photoelectron. But if the supply energy is less than 5 joule, then it will not be able to overcome the attraction of the atom and it will still remain in the atom. And in that case, that absorbed energy will exhibit itself as heat energy. It will vibrate more, it will try to get out, but it will not be able to get out. So that additional vibration will exhibit as heat energy of the atom. In general, or for the whole metal piece, it will be represented as a heat energy. So what the Web theory proposes, that whenever energy will be supplied by means of a continuous stream to a metal atom's outer shell layer electron, that electron will start to absorb that energy and start to store it over a duration of time. So as it will start to store that energy and over a duration of time, the total amount of energy within that electron increases, there will come a certain point when the energy of the electron will be higher or will match the value of work function. মানে আইডিয়াটা হচ্ছে এরকম, মনে করো একটা ইলেকট্রনের নর্মাল এনার্জি ছিল 0 জুল, আমি তাকে লাইট শাইন করলাম, এখন আমি ওখান থেকে কন্টিনিউয়াস স্ট্রিমের মতো এনার্জি দিতেছি। এখন ইলেকট্রনটা কি করতেছে, আমাদের ওই স্ট্রিম থেকে এনার্জি অ্যাবজর্ব করতেছে এবং তার মধ্যে জমা করতেছে। জমা করতে 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 একসময় তার টোটাল এনার্জি ভ্যালু 5 জুল হবে। When the electron's energy will reach 5 joule or will reach the value of work function, the electron will free itself and become a photoelectron. That's what wave theory proposes. This thing actually means this thing means multiple problem because what if this was supposed to happen? First of all, there should be some visible, some measurable, significant time delay between shining the light and the photoelectric effect, because the electron would be responsible to store the energy over a duration of time. That time might be very small, but it would take some time. But rigorous experimentation finds that photoelectric effect is an instantaneous happening. It happens instantly. That's one mismatch of the theory and the experiment and the results. The other thing is that if the wave theory was supposed to be correct, then photoelectric effect should happen at every frequency. I mean, frequency wouldn't be a problem. Frequency would not be a problem because, well, if the frequency of a certain light source is less, but if we give enough intensity, think about it. Let's say you have a low frequency light, let's say red light source, but you have a lot of those light sources. Maybe you have hundreds of those red light sources. So you have a pretty high intensity. The rate of energy flow is pretty high, damn high. The photoelectric effect should be dependent only on intensity. If you have a high intensity, I mean, if your rate of energy supply is more, in that case, you're going to have more rapid photoelectron release or photoelectric effect happening more rapidly, because you're supplying a much higher rate of energy. So electrons can reach to their work function value more rapidly. So you'll have more electrons released per second. And because the electrons will actually absorb and store that energy over a duration of time, so photoelectric effect should happen at every frequency. I mean, frequency should not even play a role in that scenario. It shouldn't, because if I have high frequency or low frequency, it doesn't matter, I'm supplying energy. So as long as I'm supplying energy, photoelectric will happen, period. It might be a bit longer, it might take a bit smaller, which will be determined by the intensity, but not by the frequency. So the wave theory proposes that frequency should not be any important factor for photoelectric effect. Intensity should be all the important factor for photoelectric effect, which was not the case for experimental observation. So this is the shortcoming of wave theory in explaining the photoelectric effect. So now comes Albert Einstein, in his hands the explanation of the Max Planck's theory or photon theory, and he starts to explain it. What he says that no, light comes from a illuminated source in packets of energy or in small lumps of energy, which are called photons. Each of those photons has a very specific amount of energy depending upon the frequency of the light source. Up till now, Max Planck's theory is just mentioned. What he says that the electrons absorb the photon amount of energy by one collision. All the photons are individually different from each other, like they are shower droplets. They are not attached with each other, because if they are attached with each other, that would mean a bigger droplet. That's not the case. All the photons are individually different from each other. So an electron can be hit by one of these photons, and whenever that happens, all the photons energy, try to understand this word very carefully, all the photons energy is given to that electron instantaneously. All of the photons energy is given to the electron instantaneously. This is really important for you to understand. The wave theory proposed that energy would be delivered continuously, little by little, and it will accumulate up. But photon theory says, yeah, no, When the photon will hit the electron, all of the photon's energy will be given to the electron in a single instance of time. একবারে পুরো এনার্জিটা সে পাই যাবে। Now, if this amount of absorbed energy is higher than the work function, then the electron will become photoelectron. মনে করো একটা সার্টেন এলিমেন্টের সোর্সের ফোটনের এনার্জি হচ্ছে, আমি মনে করো E1 লিখলাম, E1 হচ্ছে মনে করো হচ্ছে 10 জুল, আরেকটা সোর্সের E1 হচ্ছে মনে করো সরি E2 হচ্ছে মনে করো লেটস সে 3 জুল, আরেকটা সোর্সের ই হচ্ছে মনে করো এক্স্যাক্টলি 7 জুল। ওকে, আচ্ছা, ফটোইলেকট্রিক ইফেক্টের একটা ডিফাইনিং ইকুয়েশন আছে, ইকুয়েশন আমি অ্যাকচুয়ালি লিখতে ভুলে গেছি। E equals to phi plus Ke max. এটা কি ইকুয়েশন সেটা আমি একটু পরে বলতেছি, ডোন্ট ওয়ারি। So what it says, what Albert Einstein says that if the energy of the photon is equal or bigger than the work function amount of energy, work function of that electron, then the electron will utilize the work function amount of energy to make itself free from the atom, and using the remaining amount of energy, it will shoot itself out of the metal surface, thus becoming a photoelectron. আমি এই কথাটা আবার বলতেছি। If the photon energy is bigger than the work function, then the electron will use work function amount of energy to make itself free from the atom, and using the remaining amount of energy, it will shoot itself off the atom, thus becoming a photoelectron. So if it has more energy left, it will have a higher kinetic energy. If it has less energy left, it will have a lower kinetic energy. For example, for this example, if you consider what I assume that this metal piece has a work function of 5 joule. Take this number. If we shine 10 joule photons onto this surface, then out of this 10 joule, 5 joule would be used for as work function, and then as the electron shoots itself out of the surface, as the electron comes out, it will have, each of these electron will have 5 joule amount of kinetic energy, because they were each delivered 10 joule, they spent 5 joule to free themselves, the remaining 5 joule will be kept as kinetic energy. And then if we have, if in another case, if we shut this light off and use the other source which has 7 joule photons, in that case they will once again use 5 joule amount of energy, and as they come out of the atom, they will have 2 joule amount of kinetic energy. So idea is very simple. If you supply enough energy to the electron in terms of by means of photon, they will use whatever they need to use to make themselves free from the atom, which is work function, and whatever is left will be left as kinetic energy in the photoelectron. এটা হচ্ছে idea. However, if the energy of the photon is less than the work function, for example, if we have some source that has 3 joule worth of photons, in that case, this electron will absorb this energy 3 joule, and it will jump from its current shell to a much higher shell. You should know from your chemistry that outer higher shells have more energy compared to inside shells. Do you know this thing from chemistry?
Yes, sir.
Okay, so if the supplied photon energy is less than work function, in that case the electron cannot become completely free. That's not going to happen. So what is going to happen? The electron is going to jump to a higher shell immediately by absorbing that energy, and from that position it will once again instantly jump back to the original shell. So by absorbing the energy, it will jump higher, and it will not stay there. Instantly it will once again come back to the original shell, and it will give up the absorbed energy. So this is how it's going to happen. So that giving up the energy, I mean, whenever the jumping back electron will give up that energy, it can produce some electromagnetic wave, which can be in the form of infrared wave or which will actually increase the temperature of the object, which basically means if we have a source, not a source, if we have source which has a maximum photon size of 3 joule, and we use a lot of them shining upon this piece of metal X, then we'll see the metal piece getting warm up really fast. We will not see any electron coming out of it. To make us see electron come out of it, photoelectron come out of it, the minimum photon energy required is 5 joule. So we have to increase the frequency of the light source to a certain value so that the supplied photons can be at least equal to work function, at least. If it's a bit bigger, well, then obviously better. So, and you might wonder that if it is exactly equal to work function, can the electrons come out? The answer is no. If we supply to this object some photons which are let's say E4 fourth source, which is exactly 5 joule, in that case the electrons will be free from the atom, but then they will, once they overpower or overcome the attraction of the atom, they don't have any energy left. So what will do, how would they move? The answer is they would not move. In this case also, if you still want to have if you still want to capture those photoelectric effects, those photoelectrons, what we can do, we can introduce a small slightly positively charged net over here. So that's usually how typical photovoltaic cells work or solar panels work. We can use a very fine mesh of mesh means net, very fine mesh of slightly positive voltage wire, so that whenever the photoelectron is produced, it will be attracted by the positive pair, and that will be picked up immediately by the positive mesh. So that can be also done if we want to do this. It's not essential, but it's possible. I'm just saying. So this explanation seem to work out. And also like I said, that whenever the photons hit the electron, one photon can only make collision with one electron, and that's it. There's a 1:1 relationship over here, or 1:1 ratio over here. So whenever the photon hits the electron, all of the photon's energy is given to the electron immediately, instantly. So there is no question or requirement for time delay, as the wave theory would propose. Wave theory propose that there will be some required time for the electron to absorb the energy and accumulate that over the duration of time to reach up to the value of work function. Photon theory says no such thing required. If the photon, all the photon's energy will be given to the electron in the instant of collision. So photoelectric effect, if it happens, will be an instantaneous happening with zero time delay. Which is basically what we have observed in the experiments as well. So all of these things, all of this practical outcome of the photoelectric effect were successfully and logically described by the photon theory. And that's when scientists came to understand that, okay, we have to accept that light is actually a particle, because other than that, the photoelectric effect cannot be explained. Then again, the problem that happens, so এইটু পর্যন্ত হচ্ছে photoelectric effect explanation. Then again পার্টটা পড়া বলতেছি। এই পর্যন্ত কারো কোনো কোশ্চেন আছে কিনা? Anyone? Nope. আচ্ছা। Then again, light rays were still found to undergo a lot of the earlier wave behavior. Like light rays would do reflection, refraction, diffraction, polarization, and so on. So these behaviors are quite exclusive to waves. So scientists were now in a bit perplexed condition that actually how should we define light as? Should we call it a wave or should we call it a particle? This answer is still unsettled. The idea that scientists have decided to live upon is that light, when observed from different perspectives, can either work as a wave, can either look like a wave or can look like a particle. We don't know for a fact. We don't know for sure. Uh, it's something like there are certain optical puzzles. Do you know this thing? আচ্ছা দাঁড়াও আমি তোমাদেরকে একটা ছবি দেখাই। হুম না, আমি যেটা খুঁজতেছি সেটা আমি পাবো না, বোঝা যাচ্ছে। আচ্ছা ব্যাপার না, না ব্যাপার, না ব্যাপার না। আচ্ছা বাদ দিই। So what the scientists came up to decide that okay fine, light is going to light we're going to define that light works as waves sometimes, that works as particles sometimes. It will have different exhibit property depending on how we observe it. For certain experiments light is going to behave like a complete wave. For certain experiments light is going to behave like a complete particle. Even if you use the light coming out from the same light source, it's going to behave two different ways. So it's not going to exhibit both of these behaviors at the same time. I mean, whatever the physical phenomenon that you're working with, if you judge light by that matter, it can either represent itself as a wave or it can represent itself as a particle. So either of those things can happen. So এটা হচ্ছে লাইট এর ব্যাপারে আমাদের কারেন্ট প্রেডিকামেন্ট, this is how the scientists came up to decide about it. আচ্ছা, এটুকু হচ্ছে এই জিনিসটার বেসিক ডিসকাশন। এরপর আমি একটা জিনিস আলাপ করবো, সেটা হচ্ছে এখানে এই যে পার্টটা আঁকছি, যে লোয়ার যে পার্টটুকু সার্কিটটুকু আঁকছিলাম, এই সার্কিটটুকু কেন আঁকছি সেটার পার্ট নিয়ে এখন একটু আলাপ করতেছি। দিস ইজ কল দ্য ম্যাক্স প্ল্যাঙ্কস ইকুয়েশন। এটা কি প্ল্যাঙ্কস ইকুয়েশন বলে নাকি ফটোলিটিক ইকুয়েশন বলে? দিস ইজ হোয়াট ইউ কল দ্য ফটোলিটিক ইকুয়েশন। জাস্ট এ সেকেন্ড, এক মিনিট, আমি একটু ব্রেক নিয়ে আসতেছি। আই নিড টু ইউজ দ্য ওয়াশরুম ফর